How are you all doing this morning?
Pretty good. How about you?
Doing well. Anybody have any questions? I think what was covered in the video lecture for today should hopefully have been almost exactly reviewed from Circuits 1. So anybody got any homework questions or anything that needs clarifying?
For the design problem for homework 3, is it just there's some freedom with it with as far as power supply goes? Or does it?
Let's see.
I used 5 and 0, and I checked in LT Spice and that worked out. But,
yeah, so 5 and 0 would be the correct power supply choices because
okay.
you're trying to make an analog to digital converter, and so your digital signal should be 5 volts when it goes high and 0 volts when it goes low.
Okay, thank you.
Mm-hmm. Anything else?
Dr. Hartman?
Yes, ma'am.
I don't quite have a question about the homework right now, but I was wondering if it would be, I think I'd find it more beneficial if we did like a small review over the lecture material before classes. Is that something that could be implemented into the next lectures? I don't know. I'm just thinking like a small review over the material, like a recap. Before classes begin. I don't know. I'm just.
No, I'm just. What do you mean? So, like, do you want to use this time to recap stuff? Is that what you're saying?
Yes, sir. I was wondering.
No,
I don't know if the other
there's-
students would feel that same way, but I feel like a nice kind of like a summary over the material that we should have studied before class kind of
Okay.
it would be beneficial.
Yeah, I don't have any problem with that. But I mean, I guess my question then is like, what? Like, I want to use this class time to help you guys with anything, with any portion of the class that you feel. I don't want to say necessarily that you're struggling with, but that just, I guess isn't quite clicking. So like, help me figure out what exactly it is that you're looking for review over. Like, is it applying the ideal op amp rules? Is it how to identify the different types of op amp circuits? Some combination thereof? Is it from previous material that's not quite clicking, or does any of that make sense?
Yes, sir.
Yeah, I mean, I'm happy to use the full hour and 15 minutes to do whatever it is that you guys want of me. I got no problem there. I just need better direction, I guess. So, like for today's material, I think the lecture that was posted online was all about common op-amp circuit topologies. Is that correct? Specifically,
Yes,
negative feedback ones.
Yes, sir.
So what about that lecture do you need help with further understanding?
So I'm not gonna lie. I spent the whole weekend moving back to Ruston, and so I'm just behind on lecture 5. I didn't quite have time to actually listen to it this weekend.
Okay.
But so I do apologize for that. But
no, the stuff comes up, and I'm trying to be real fluid and accommodating here, so that's not a big deal at all. So, all right. So
I don't have any questions about this one. I just realized I was just struggling a little bit with the other homework, just kind of refreshing my brain on some of the material. I understand now, but when I was just thinking about it, I think it just for, at least for me, I don't know about the other students. I would appreciate like a recap. I can come with questions more so in the future, but
Yeah, so questions would help me to direct the issues, because I mean, like I'm trying to think about this. You know, the videos are there, and we're going this route with using the pre-recorded videos so that, you know, if something seems, I don't want to say odd or whatever, but if something, you know, if something seems a little wonky or whatever, you can rewatch that section, and, you know, sometimes that may clear things up, or sometimes that may help you articulate a question better.
Yes, sir.
So yeah, in the future, having questions prepared for this section would be great. But today, let's take a run through of some examples and catch you up. Okay.
Okay, thank you. I apologize. I was moving in all this weekend, and I just didn't have time to watch the lecture before class.
Not a problem. All right, let's see, because I'm sure the 7 people that aren't here will probably come up with something, or this could be beneficial to them as well. All right, so let's start with, let's see. Change my pen color. Simple-ish circuit. At least it's intention for it to be simple. All right, so we're going to look at this circuit here first. It's a generic circuit, no numbers or anything involved. But there are a few things that I would like to point out, okay? So because it is a negative feedback circuit, and we can see that it's a negative feedback circuit because a resistor exists between the inverting input node, which is right here, and the output node, which is right here, we have feedback. And because it's between the inverting input node and the output node, it's called negative feedback, all right? So anytime that we have a negative feedback op-amp circuit, hopefully we've proven to this point that using the ideal op-amp rules where, sorry, the ideal op-amp parameters are that Rn is effectively infinity ohms, R out is effectively 0 ohms, and our open loop voltage gain is effectively infinity volts per volt. These lead us to some ideal op-amp rules that we can apply to make our circuit analysis easier, so that we don't have to go back to the practical model and deal with all that. Oh wait, no, not parameters, rules. Well, my pen thing isn't writing. First rule being that voltage drop can occur between input terminals. And the second rule being no current may flow into the input terminals. These two rules and effectively nodal analysis are all that's needed to analyze really any op-amp circuit. So applying our ideal op-amp rules, the voltage difference between the input terminals must be 0 volts because no voltage drop can occur over them, which means that whatever voltage we have here at the non-inverting input terminal, which I'm going to call V+, I'm going to use a different color for it, must also appear at the inverting input terminal up there. So V+ and V- must represent the exact same voltage. And we also have our constraints. No current can flow in or out of either of these input terminals. So let's see. So if we apply those rules, what is the function of resistor R3, or does it contribute anything whatsoever to the circuit? So let me rephrase this question then, since nobody's piping up with anything. What is the current flowing through the resistor R3? Do we have enough information to figure out what that is?
Is it no current? I don't.
That's correct, right.
Okay.
So there's this resistor is connected the resistor R3 is connected directly to the non-inverting input terminal. And since no current can flow into either of the input terminals, that means that no current can flow through the resistor R3. Does that make sense? It's like a series connection with no current flowing through it. No current can flow through either of the elements, effectively. One of the elements being the resistor, the other element being the input portion of the op-amp. So if no current flows through resistor R3, what voltage drop occurs over resistor R3?
None.
Thing.
Or
So I heard none, and I believe I heard dang. So the answer is none. Using Ohm's law, right? Ohm's law, V is equal to I times R, so it doesn't matter what the resistor value is there. If I is 0, then the product of 0 times the resistor value is 0. So there's a 0 volt drop here, and since I've indicated the current flowing effectively up through the resistor, I'll draw it like this. So using the information that we've collected so far, what is the voltage present at the non-inverting input terminal? So what is the voltage that I have labeled as V+? What's its numerical value?
Zero volts.
Right. So even though there's that tricky resistor there, this op amp is going to behave, if we treat it as an ideal op amp, it's going to behave as if the non-inverting input terminal were directly connected to ground. So someone who isn't Sadie, what is the voltage at the inverting input terminal going to be? That's the voltage that I've labeled as V minus. So if we apply ideal op amp rule number 1, where it says that no voltage drop can occur between the input terminals, that means that V plus and V minus represent the same voltage because there's no voltage drop. So we can effectively just follow Kirchhoff's voltage law, make a KVL loop along this path, and still find that V minus must also be equal to 0 volts. So that's the successful application of the first of our ideal op amp rules. All right, so everybody with me thus far?
Yes, sir.
Okay. So if our input voltage signal Vn is non-zero, so we're measuring some signal, there should be a potential difference over resistor R1. So what I'm saying is if Vn is not 0, then the voltage present on the left-hand side of resistor R1 is not 0. And the voltage present on the right-hand side of resistor R1 is exactly 0. There's some difference in electric potential, right?
Yes.
Yes, sir.
Okay. So what happens when there's a difference in electric potential or a voltage drop over a resistor? So if I took a resistor out of a package, no current's going to flow through it. But if I connect one end of the resistor to the positive terminal of the battery and the other end of the resistor to the negative terminal of the battery, what's going to happen to the resistor?
It's going to get current.
Yes. So current must be flowing through this resistor, R1, for any non-zero input signal. So I'm going to label this current I. Now, Kirchhoff's current law applies all day, every day, in every situation, because if it doesn't, then we violated the law of conservation of charge. So the current that flows through resistor R1, that I've labeled I and put with a blue arrow, is going to flow to this node point, the inverting input terminal. Where is it going to go after that?
Up to R2.
Right. All of it has to go up through R2 because none of it can flow into the non-inverting input terminal because of ideal op amp rule 2. So all that current I is going to flow through resistor R2 as well. And those currents are identical. They might be, we can identify them with different mathematical expressions, but their numerical value has to be exactly the same because they are representing physically the same current. So can we write a Ohm's law equation for the current that's flowing through resistor R1 in terms of Vn?
Are you wanting to do nodal analysis, like for the whole thing?
So we could go that route. So we could perform nodal analysis at the inverting input node and get the relationship that I'm looking for here. So let's go that route then, since that's something that you suggested. All right, so we're applying KCL at this node. So we're going to have the current directed to the left through resistor R1 added to the current directed to the right through resistor R2 is equal to 0. And we're going to try to express those currents in terms of our input voltage and our output voltage. So the current flowing to the left through resistor R1, how could I write that?
That's going to be your V minus minus Vn over R1
All right, what about
plus your V minus minus whatever you want to call the other node over R2.
So I would call that V out because it's already labeled.
Oh,
V.
yeah. Yeah, it's V out.
Divided by R2, okay, is equal to 0. But we already know the numerical value for V minus, so we could substitute that in, right? So it's going to be negative Vn over R1 minus V out over R2 is equal to 0. And we can rearrange this so we can move negative Vn over R1 is equal, to V out over R2. And then from this, we finally get negative R2 divided by R1 multiplied by, sorry, that should be Vn, is equal to V out. So this is our fundamental relationship for this particular type of op-amp circuit. So as long as we know what Vn is, and we can determine the ratio of the resistors, the feedback resistor divided by that resistor R1, we can figure out what our output voltage is. So I have another question then. Does the value of resistor R4, assuming it's not 0, meaning if we put a short circuit there, that's obviously going to force the output voltage to be 0 because it will be directly connected to ground. But as long as R4 isn't 0 ohms, does the value of the resistor R4 affect how our op-amp behaves using the ideal model?
No.
No, sir.
Correct, yeah. So this resistor R3 effectively doesn't do much of anything to our analysis, and this resistor R4 also doesn't really do much of anything to our analysis. There are practical reasons why we include them in real op-amp circuits. So that resistor R3 exists to limit what's called input bias current, which effectively just means that when you have a real op-amp, there are errors in the manufacturing process which can cause very, very small currents to flow on the order of nanoamperes. And that current limits, or excuse me, that resistor limits those currents from effectively propagating through and giving you an erroneous output signal. And that resistor R4 exists as effectively a load. So it's what you're applying your signal to. That could be, let's see, so your input signal would likely be from a sensor. So your output signal might be applied to some type of measurement instrument that has a characteristic impedance. Now in real op-amp circuits, if the value of resistor R4 is on the order of the output resistance of the practical op-amp model, it can cause some issues. So hopefully I've done this in most of these problems. I think I have, yeah. So I typically always use kilo-ohm size resistors in designing all of my op-amp circuits, kind of regardless of whatever op-amp I have. And the reason is that a kilo-ohm size resistor is effectively in the sweet spot. So if your resistors are too large, it's going to cause issues with biasing, and if they're too small, it's going to cause issues with what's called clipping. You're going to exceed the output power limit of your op-amp if your resistors are too small. But we're worried about practical op-amps right now, so that's nothing that you really need to worry about at this point. Okay, so we've developed a fundamental relationship between the input voltage and the output voltage. We can express that in a slightly different way by a term what's called the closed loop gain. So AV, I usually write it as AV. You may also see it as AVCL, so closed loop gain, and that is defined as the output voltage divided by the input voltage. And for this particular, oh goodness, what happened? This particular op-amp, that's simply the ratio hold on, my computer's freaking out. I don't know why it's just making that noise over and over again. What on earth is happening? All right, let me see. All right. It actually saving which one great it did. All right. A little bit, but it's not a big deal. All right, so what I was saying was we now have a relationship, the closed loop gain defined as V out divided by Vn is negative R2 over R1 for this particular type of op-amp circuit. So it's actually no longer necessary for us to even do circuit analysis on something like this, right? If we're only interested in, say, the output voltage of the circuit, as long as we know what the input voltage is, the resistor R2 value and the resistor R1 value, we can figure out what V out is without performing any analysis whatsoever. So this is a very powerful bit of information to have. And what the remaining part of the lecture, the common operational amplifier topology lecture does is give you or go through the derivation of the input-output relationships for several different types of op-amps. But this process that I've used in this example is the exact same for all of the circuits. So just to reiterate, what we did was we applied the ideal op-amp rules. So ideal op-amp rule 1 came from, or was applied, let's see, here, where we said that there was no voltage drop that can occur between the input terminals. Ideal op-amp rule 2 was applied here and here, where we say that no current can flow into either input terminal. Then we simply used nodal analysis at this non-inverting input node and was able to, we were able to get a relationship between the input voltage and the output voltage. So give me just a second and we will go through this, a similar thing with a more robust circuit. This will actually kind of lead into what we're going to be doing for tomorrow's lecture. So let me find this. Sorry, that's backwards. All right, so this is the circuit that we're going to be trying to analyze. And I'd like to point out two things. The first of which should be fairly obvious. There's more than one op-amp in the circuit. And that's actually not really going to influence the way that we approach this problem at all. The second thing is that it's fairly obvious to see that this op-amp, which I'm going to call A2, has negative feedback. Because an resistor is placed specifically between the negative inverting input terminal and the output terminal of the op-amp A2. The op-amp up top, A1, does not have a specific negative feedback resistor. Like so, there is not a single resistor placed between the output terminal and the inverting input terminal. Instead, it's a series of resistors, but that's still satisfying the role of a negative feedback path. So there's definitely not positive feedback because there's no resistor connecting the non-inverting input terminal to the output, and it's not an open loop system, so it's got to be negative feedback. All right, so the first question that I'm going to ask then is, what is the voltage present at the non-inverting input terminal of the op-amp labeled A1? So I'm looking for this voltage. I'm going to call it V1 plus. What's that voltage value with respect to ground?
10.
10. Yeah, nothing particularly crazy about that. There's a 10-volt source placed between this node and ground, so that voltage with respect to ground should be 10. So what about this voltage, which I'm going to call V1 minus?
I would gander also 10.
Right, it must be 10 as well, because there cannot be a potential difference between the inverting input node and the non-inverting input node for a negative feedback op-amp circuit when we're using the ideal laws. And hopefully you found when we're using the practical model that the difference there is on the order of a few millivolts at best. So this is also 10 volts, okay? Excuse me. Let's do a similar treatment for the amplifier A2. So let's call this voltage V2 plus. What's this guy going to be?
0.
All right. So then V2 minus here will also be
0.
0, yeah. So, excuse me, my dogs are being jerks.
My dog hears that.
All right, so we've successfully applied op-amp rule number 1 to both of our op-amps. So let's go ahead and apply op-amp rule number 2, which says that this current is going to be 0 amps. This current is going to be 0 amps. This current is going to be 0 amps. And this current is going to be 0 amps. So with those constraints in mind, what is the current flowing through this 2 kilo ohm resistor?
It's to 0.
So what's the voltage drop across that 2 kilo ohm resistor? All right, so let's choose that color. What's the voltage present with respect to ground for this gray node?
10.
Okay. So what's the voltage drop over the 2 kilo ohm resistor?
10.
Oh, okay. So I is going to equal 10 over 2,
Okay,
2K.
right. So that would be 5 milliamps.
Oh, my calculator on me.
10 divided by 2000 is 10 divided by 2 times 10 to the minus 3. Yeah, 5 milliamps. Great. All right, so that was a little bit more pulling teethy than I wanted it to be, but that's okay. What must this current I500 be?
$5 milliamps.
You're correct, but why? Well, actually,
Because
not quite correct. You're very close, though. So explain your reasoning.
shouldn't the current have to go that way because no current goes into the inverting terminal?
Right, so if no current can flow up into the inverting terminal, if we apply Kirchhoff's current law at this node, we should be able to figure out that I500 has to be negative 5 milliamps, right? Because the sum of the currents has to be 0,
Yeah.
and they're all exiting. So that's why I said that you were very, very close. You get the magnitude right, but effectively the direction wrong because we missed the sign there. All right. So let's see what do we have here. So to recap, we know that this is 10 volts. So what's the voltage drop? Or actually, I guess it would make more sense. We can get rid of this negative sign by changing the direction on that guy, which might make things a little easier for us. And so I'm going to put a positive and negative sign. So what's the voltage drop over the 500 ohm resistor?
Point 0.5.
All I heard was 0.5. Did I miss something?
2.5.
Great, thank you. All right, so 2.5 volts. That's correct. Okay. So what is this voltage? Actually, let me rewrite this. V2 out with respect to ground. So we're trying to find the voltage present from effectively this point to out, like so, plus here, minus here. How could we do that? All right, so nobody's saying much of anything. A little bit disheartening, but it's okay. Okay, so we have effectively a situation where we have 2 kilo ohm resistor, and we know there's a 10 volt drop over it. And then we have over here, draw better, a 500 ohm resistor over which occurs a 2.5 volt drop. I'm trying to find this voltage. How do I do it?
7.5.
No.
No.
But what circuit analysis tool did you attempt to use there? Let's start there.
Well, in voltages in series can be added.
Okay, so
And
when you're adding together voltages, you are inherently using Kirchhoff's voltage law. Okay. So if we apply a KVL loop around this guy, we would see negative 10 volts minus 2.5 volts plus V out is equal to 0. If we're starting in the bottom left-hand corner, we see the negative polarity voltage of the 10 volts, the negative polarity voltage of the 2.5 volts, and the positive polarity voltage of the out. So that's where these signs came from. So I can rearrange this, and I would find that V out is 12.5 volts. So you said that you can add voltages together when they're in series, and that's absolutely true. What you failed to observe was that these voltages have the same polarities,
oh yeah.
not opposite polarities, so they should have added together directly. So V out 2 must be what?
It has to be the same.
Yeah, because we're doing the exact same calculation. So it's 12.5 volts. Okay. So there's 12.5 volts here because there's a 2.5 voltage drop from here, from this point to this point, and then there's a 10 volt drop from this point to ground. So that's why V out 2 with respect to ground must be 12.5 volts. We just add up the voltages until we hit ground. Alrighty, so this current through the 5 kilo ohm resistor, how can I find that?
It's still just going to be your 5. No, it's going to be -5. The arrows the other way.
So you are incorrectly applying op-amp rule number 2. Let me explain why.
Okay.
Op-amp rule number 2 says that no current may flow into or out of the input terminals of the op-amp.
Okay, so but it can flow into the output.
Exactly right. So yeah, you just
Okay.
made an assumption that you know anything about what's going to flow out of the output terminal, and that's one of the biggest drawbacks of the ideal op-amp model versus the practical model, is that we have no means by which to tell how much current is going to flow out of the output terminal. As it turns out, it will just be whatever needs to. So if we can't simply follow the current, what do we need to do? So we know the voltage with respect to ground on this side of
Yeah,
the 5 kilo ohm resistor.
12.5 minus 0 over 5K.
There we go. So 12.5 divided by 5 is 2.5. 2.5 milliamps direction right?
Yeah.
Oh my
Yes.
God, what did I just do? Okay. So what's this current through the 750 ohm resistor?
So this time it's still gonna be 2.5, right?
Is it going to be positive 2.5 or negative 2.5? Do KCL at this node. So 2.5 flows in, so 2.5 must flow out. You're right.
Yeah.
Don't
Okay.
you need to know why you're right. Okay. So then that begs the question, finally. What this output voltage is, right? So this voltage that I've labeled V out here with respect to ground, which is how I've defined it in this blue bit here, is going to be what? So if we drew a KVL loop from this ground here to this ground here, right? There's no potential difference over the input terminals of op amp A2. So all we would see would be the voltage drop over that 750 ohm resistor. So let's see, current flowing into the positive polarity terminal, so it's absorbing power. So let's see, V750 plus V out is equal to 0, doing KVL around this loop. Everybody okay with that?
Yeah.
As long as I start at ground and end at ground, it is entirely irrelevant what path I take. I know that this voltage drop, is 0 volts. So this point right here is effectively ground as well. So all I have is the voltage drop over the 750 ohm resistor, positive polarity on bottom, plus the voltage drop V out is equal to 0. So what's V, so let's see, so V out is then negative V750. So what is the voltage drop over the 750 ohm resistor?
Over the
Polarity on the
750
bottom.
is 1.88 volts.
1.88, okay.
Yeah, so your V out's gonna be negative 1.8.
2.5, so probably 1.875, but whatever.
Yeah.
All right, so that problem was significantly more difficult, I think. Hopefully refreshed you guys a little bit on how to apply KVL and KCL. But we were able to solve it just using the same basic steps, right? We kind of broke our nodal analysis up into piecewise bits. So instead of say fully applying nodal analysis, we just did KCL at all of the different nodes, which if we had done them all simultaneously, that would have been nodal analysis. But the way that things worked out, we didn't need to do them all simultaneously. We were able to get individual bits and apply them back and forth. All right, so that is, like, the question that we just analyzed there is probably harder than anything I put on, definitely harder than anything I put on tests, and I believe it's harder than anything I put on the homework in quite a while. So I guess my question then is, are you guys feeling a little bit more comfortable applying the ideal op amp rules?
Yes.
Okay.
Yes, sir.
Wonderful. Does anybody have any further questions regarding applying the ideal op amp rules and all that kind of good stuff with regards to any of your homeworks or anything like that?
I guess just for homework in general, so the homeworks correspond to, you know, their lectures. There's no homework for lecture 5, right?
That is correct. So if you look at homework 4, actually, let me see. I think I can just open it up in here. So the first problem of homework set number 4 asks you to use the practical op-amp model and determine various values of things. And it's extraordinarily similar to the example problem that I worked in the pre-recorded bit for what I called lecture number 4, I believe. Or the lecture about where the ideal op-amp rules and all that stuff came from. So it would have been last Thursday's pre-recorded lecture. Problem 2 jumps into using the ideal op-amp model, determine the output voltage. So this is more in line with what we've done today during this session. So for instance, this guy right here might look, and it's not might, it probably does look very awkward and mildly terrifying, but you could do a source transformation here, and instead of having a current source in parallel with a resistance, you would have a voltage source in series with a resistance. You could similarly combine this 17K resistor and this 500K resistor because they are in series. And something that a lot of you guys, not you specifically, but previous Circuits 2 students have missed, this 5 kilo ohm resistor and this 10 kilo ohm resistor are also in series. So you could combine them. So you would be left with an op-amp circuit that looks something like this. Let's see, so this is, it's got negative feedback, and this is the out. So with a couple of simplifications, you can get a circuit that's looking like this, where I've made 2 assumptions here at the output. The first of which is that, so let me be clear here. The output voltage that we are trying to find is the difference in electric potential between this point and the ground. And that may or may not be the same thing as the voltage present at the output terminal of the op-amp. Now in this case, it is going to be, because there should be no current flowing through the 50 kilo ohm resistor, because it's not part of a closed current carrying path. Does that make sense?
Yes.
So I'm saying this voltage must be 0 because no current can flow through that resistor. So all you're asked to do then is to find the output voltage of this op-amp configuration, which I feel very strongly that you should be able to do by now, based on what we've done today. It's not quite going to be a differencing amplifier, which is one of your common op-amp topologies because it's missing that resistor there, but it'll be pretty similar. It's going to have something to do with the difference between the voltages, but it's not going to be as simple as V2 minus V1 or whatever. And then finding the current, the output current of this op-amp is just going to be done using Kirchhoff's current law at that node. So this problem is very in line with what we've covered for today. Same thing here, using the ideal op-amp model, calculate V out for the circuit below. And then this guy right here is probably more closely aligned to the common amplifier topology pre-recorded lecture. So in the pre-recorded lecture, I think I did circuits with capacitors. This is one with an inductor where you're just trying to find the input-output relationship for any input voltage Vn of t. So the reason why I underline that is because some people think that any input voltage means a sinusoidal input voltage. That's not true. I mean literally any input voltage. So if you have omegas and stuff thrown in your equation for this problem, you're very, very wrong. You're finding a subset, the solution for a subset of any input voltage. So I want you to go through this in an extremely similar fashion to either the integrator or differentiator op-amp circuit in the common negative feedback op-amp topologies video lecture thing, and apply the basic principles of solving any negative feedback or negative feedback ideal op-amp circuit. So find the voltage at the non-inverting terminal. Use that to find the voltage at the inverting terminal. Find the current through here. Find the current through here. Set those currents equal to each other, and then figure out what V out is. All right, and then the last problem is a design problem. And let's talk for a moment about this. So you're asked to design an op-amp based converter circuit with supply voltages of plus or minus 12 volts, which will convert a 4 to 20 milliamp input current into a 0 to 5 volt output voltage. And then we're going to verify that our design behaves as required using LT Spice. So, to be clear here, when when the input signal is 4 milliamps, the output voltage should be 0 volts. When the input signal is 20 milliamps, the output voltage should be 5 volts. Now, I give you a hint that the converter portion of the circuit should be a practical current source, which converts the input current into a voltage drop over an appropriately sized source resistance RS. So my question for you guys right now is, how many of you remember what a practical current source is?
Is that a current source in parallel with a resistor?
That is absolutely correct. So we have a current source that's going to range from 4 to 20 milliamps in parallel with some resistance RS. And we are going to, so we're going to have a situation like this. So this is the converter portion of our circuit. So I'm going to call this VCon. Okay. So I have a question for you guys to think about. Is there any way that my low end current, so the 4 milliamps of current, is going to generate an output voltage of 0 volts?
Dr. Hartman, can you repeat the question?
Sure. Is there any way that, so this 4 milliamps of current, let me change this color here, right? So this 4 milliamps of current is going to flow, and then it's going to see the resistive path down or the open circuit to the right-hand side, okay? Which means all that current is going to flow through that resistor RS. It's just going to flow in this little loop. So my question to you guys is there any value of RS that is going to convert the 4 milliamps of current to 0 volts?
If you short it,
Okay, but if there's a short circuit there,
can't do. What else do you do?
the 20 milliamps is going to be is also going to be
Okay.
0 volts. So you're not
All of it.
converting your current into a voltage, right?
Yeah.
Yeah, you're just shorting it out. So the only one that works to get to for 4 milliamps to give you an output voltage of 0 volts is 0 ohms, a short circuit, but that messes up what's happening effectively when the current goes high. So when it's 20 milliamps, if the RS value was also 0 ohms, then the converted voltage would still be 0 volts. So that's violating our design constraint. Does everybody understand that?
Yes.
Okay, so is there a way to make this voltage have a difference of 5 volts? So instead of making it range from exactly 0 to 5 volts, which I can't make it do, could I make it range from, say, 5 volts to 10 volts or something like that?
Yeah, and use a difference.
Follow your thought through.
Oh, make a difference amplifier.
Right. So what Sadie's got is effectively the gist of this problem already. Okay. So the first thing when you're approaching this design problem is that you have to realize that there's no way to make the output go to 0 volts without figuring out a way to subtract some voltage. And that's where the op amp comes in. So you're going to use either a differencing amplifier, which is going to be fairly straightforward, to literally just subtract a voltage offset, or you could, if you've felt squirrely, instead use a summing amplifier and add in a negative voltage. Either way accomplishes the same thing. The key here is that you have to get rid of some voltage. So let's talk real briefly before we wrap up here about how to select this resistor value RS. Okay, because it's integral with doing this in the most simple way possible. Meaning that if we can choose the value of RS such that we get a differential voltage of 5 volts, depending on whether we're at 4 or 20 milliamps, then we really only have to have amplifier gains of effectively 1 going through things. So Ohm's law says that E is equal to IR. Everybody on board with that?
Yeah.
Yes, sir.
So I would argue that since we know what the differential voltage is, and we know what the differential current is, that's going to give us the resistor value. We have a known change in voltage at our output, and we have a known change in current at our input. So that should allow us to calculate RS pretty easily. Make sense?
Yes.
Okay, that's all I got for you guys today then. I feel like that was a hesitant yes, but I'll take it.
Sorry, I'm writing.
No, it's not. So there's students have continuously asked me, oh, I don't know how to solve or to figure out what size resistor I need, and it's Ohm's law. That's simple. You guys get all worried about the details and forget the basics. All right, well, I'm gonna wrap this up because my wife is calling me, so I will catch you guys later.
Thank you.
Yep, have a good day.
You
You
too.
too.